We're going to look at titration curves, and in particular here for IB high-level chemistry, but just telling us a lot more about titrations and how we can analyse the data we get from them. And so regular titration equipment here, you can pause to complete the fill in the spaces. And a couple of answers there. This one's a regular titration whereby you can find the endpoint, and we're going to look at some more vocabulary and look into them in more detail. So for this one, we're going to use a Vernier pH probe, collect data on a continuous basis on a laptop, and we're going to start with an exact volume of a strong acid measured in a pipette with 2 drops of an indicator. Then we're going to add an alkali, and for this one we're going to use sodium hydroxide, a strong alkali. So our equipment will look slightly different here, where we're measuring the pH with a pH probe. And what are you going to do as you are doing this experiment? We're going to look at the dissociation constants, going to choose an appropriate indicator and use with digital data collection more advanced instrumentation. And so we're going to look at shapes of pH curves depending on whether it's a strong acid with a strong base or a strong acid with a weak base, etc. And at the moment we're only going to look at a single proton in the acid. Going to end up with a curve with an equivalence point, which we might have called an endpoint at one time, but we want to be much more specific. And here we're going to start with 50 centimetre cubed 0.1 molar HCl and add 0.1 molar sodium hydroxide. As you do this, determine which is obviously the acid, is it strong or weak, and ditto for the alkali. And so with the lowest pH here, it's going to be the acid, the 50 centimetre cube that you're starting with. And as you add the alkali, there's a little slight increase here, but because the concentrations are the same, you get a big inflection point through the equivalence point, and then as you add more alkali, you then get the maximum here tapering off and virtually a straight line again. And so some questions here. Pause to answer or to read the answers to these questions, because number 1 here is where the pH of the original solution cuts the x-axis. Then for number 2, halfway across the bottom of the graph there, called a buffering region, which is more important with weak acids and indeed weak bases, and called the half equivalence point, but only important for weak acids which have an equilibrium constant, a Ka, an acid dissociation constant. Strong acids are fully dissociated. And so you've got the inflection of the small change in volume of sodium hydroxide added, and a vertical line there, and you're going to pick the equivalence point helped by data from the Vernier probe, and remains flat at the end because you now have a salt as the product of the acid reacting with the base, and you're adding excess base, and that pH is going to stay constant. And so what's equal at the equivalence point, where your moles of acid equal moles of base, and here it's a 1-to-1 ratio, really need the equation here, and all of the acid has been neutralized by the base at that point, and depending on the indicator that you use, that will be the color change of the indicator, but the actual pH value from a probe, pH probe, is more significant. And so what is the salt that's in the solution? And is it acidic or basic? Well, if you have a strong acid and a strong base, you're going to have a neutral salt, so pH 7. If you've, as we'll see, the pH of your salts will depend on the combination of weak and strong with the acid and the base that you're adding. So that one, the dotted line, is a strong acid with a strong alkali, and we're going to look at a weak acid. We're going to add it to this graph, and that's what you've got. So for number one, the pH of the weak acid is higher because the hydrogen ion concentration is lower. And the half equivalence point, the pKa, is when you've added 25 centimeter cubed of the alkali, and that's going to equal the pH. So if you can read the pH off and then antilog it, you'll get Ka, the acid dissociation constant. And if you look at the black line there for the weak acid with a strong alkali, the equivalence point is higher than it was for the strong acid, strong alkali. And we're going to look at the mathematics of the buffer region and the half equivalence point because your Ka for a weak acid, it's the equilibrium expression of the hydrogen ion and the anion of the acid over the undissociated acid. And at half equivalence point, your undissociated acid, HA, will equal the anion of the acid concentration. And then the equivalence point here, the salt is from a weak acid and a strong base, so the salt is going to be basic, pH above 7. And here we've got 50 centimeter cubed of 0.1 molar ethanoic acid reacting with 0.1 molar sodium hydroxide, and draw a titration curve and determine which indicator you will need for the equivalence point. And here we've got a weak acid with a strong base, just like the one we've talked about earlier. So you've got your equivalence point greater than 7 there. And so here you've got your axes, and pause to draw and answer the questions. So titration curve for 50 centimeter cubed of HCl, reacting with 0.1 molar ammonium hydroxide. And so here we have another one where you have to explain the graph here and look at what you've got. You've got methanoic acid, a weak acid, and you've got a strong base here. And go through vocabulary. It asks for you doing the 3 hardest there. Make sure you know the other ones as well. And review the titration vocabulary. Now, if we were looking at the LoggerPro data, this is the type of graph that you would have. This was just done with smaller volumes of acid added, because look, the pH is just under 13 there. And what we want you to do is to pause and answer the questions here before you go on. So you've got a few of the answers here. Which ones did you ace? Did you get correct? Which ones do you need to work on? And so for this one, you've got a strong acid and a strong alkali, so you can name those ones. For the second graph, pH starts just above 10 and goes down to about 1 point, quite a lot, and is asking you for the same data. So read those questions, pause to answer them. And again, pause to look at the answers. Again, it's important to analyze first, have you got a weak acid or a strong acid that are reacting? The pHs on the graph will tell you that. Number 3, again, pause to see what the answers are going to be there. Hopefully you'll be reinforcing the strength of the acid or the alkali that are reacting. Look at, can you identify clearly an equivalence point? And finally, the 4th one here, and last of these curves, to work through, pause to answer all of those 5 questions, please. And looking at this with a strong base and a weak acid, so name those. And then we're going to go through a number of other questions where you've got an acid and a base, and you can decide here that it's going to be a strong acid and a strong base reacting in a 1-to-1 mole ratio. So you want a monoprotic acid like HCl or HNO3 strong acids to answer those questions. So pause to be able to do those. And each one of those questions is just looked at in slow time. So you can pause as you go through those to answer them. And finally, why is the knowledge and understanding of titration curves important? And for some of that, with the weak acid or looking at the half equivalence point, determining the acid dissociation constant, etc., by graphical means, and see what else you can come up with too.